think it's page 250. Where
250?
Not 250. Never mind. It's-
254.
That's where the solution is.
Op-amp, what?
4.31. The chapter.
Yeah, I got it.
Okay. And so I think you worked it in class already, but the solution that you posted had a different answer, and so.
We'll do it. I mean,
Okay.
the solutions can be wrong. I'm just gonna tell you that. I can't vouch for everyone. It's a solutions manual. For this one, you're gonna have to help me here.
You have,
Markers are challenged these days. This is 4.31. And as I recall, I looked at it just a second ago, that's negative, that's positive. We're gonna have this basic configuration. I'm gonna put both resistor and capacitor coming down. And I'll call that R1. And then they have a second R2 here, right?
yes.
And then they have this, and then they have this going to a power or a voltage source, plus the minus VN grounded. Is that right?
That is correct.
All right,
yes.
now, we did this problem, but it's beneficial sometimes to go through them again. Key thing when you do with an op-amp problem, if you listen up, this will help. You look for two things. You know there's no voltage difference across there, there's no current into it. So you try to peg the voltage at one of these two terminals if you can. I've got the voltage here as VN, therefore I know this is VN. Correct, class? Once you have that, next thing you look for is currents. If I know that voltage is between here and ground, and therefore I know this current, and I'll label that as I1. I know that's going to be simply VI divided by this impedance. That impedance would be R1 plus 1 over CS. Remember, we work in the S domain, so the impedance of the capacitor is 1 over CS. There are no initial conditions with these. So you can throw out anything that has to do, if it's a derivative, anything that has to do with the initial conditions when you do the Laplace transform. Now, we have this basic thing, and I know I1's that, correct, class? Therefore, if I1's that, I know I2 here, or really it's the same, it is I1. That's the only place that current can come from, correct, class? Nothing can come in and out of that negative terminal. Once I have this voltage as well. I know that voltage is just I1 times R2. Does everybody agree with that? That's I1 times R2 is equal to VR2. Now if I want the output voltage, right here, here's what I'm going to do. If you just think about this, this should make sense. I'm going to take this current, and I'm going to multiply it by this impedance plus this impedance, because the voltage from here to here is really the current times the net impedance. Does this make sense to everybody? All right, so I'm just going to say it up here that V out was equal to I1, which is V in, over R1 plus 1 over CS times, now it's going to be R2 plus R1 plus 1 over CS. There's obvious cancellations coming, but I wanted to make sure you saw the entirety of it. Do you all agree with me, class? Now we go ahead and we simply simplify as best we can. When I take a look at this, I'm going to expand this and say that V out here is equal to V in times R2 over R1 plus 1 over CS. Plus, and then when I look at the remaining term right here, that divides right into that, so it cancels. Can everybody see this arm? You all put it back around that? So if I know that that cancels, it's just plus V in. Or really, I can say that this is V in times R2 over R1 plus 1 over CS plus 1. I want you to make sure you can see that with me. Make sure you see what I've done. How many agree with that? And if I make a mistake or you don't understand something, do not be afraid to ask. Yeah.
So would it just be fair enough to say that it'd just be the current times the resistance of R2 plus VI?
Absolutely. As a matter of fact, that's, you can see, you can go from here to here plus that. I did it that way only to show you a different option. You can do it, and you know, there are many times, many ways to get to the final answer. especially when you get more complicated circuits where you're given a choice between Thevenin, loop, nodal, there's so many techniques you can use to get to the final answer. They all result in the same thing, but there's different methods, yeah.
I was just gonna ask you, could you repeat what he said? I didn't catch that. About the other way to do the voltage.
Well, he said, sure, he said, what if you just went from here, ground here, add VI here, and then say plus this voltage, which would be R2 times I1. That's effectively what I've done there. It's just I took the route where I multiplied the whole current times them. They're the same thing. Now when I look at this, I'm gonna simplify it some more, and I'm gonna work from here. Everybody see what I've done so far? I'm gonna go ahead and multiply top and bottom by S here. And so I have an S there, get rid of that. You can see what I'm up to. And now because I want the coefficient there to be 1, I divide top and bottom by R1. You all see this, class? And if I divide by R1, now I get this. Here I'm just trying to manage things, make them a little neater. Now I'm gonna go ahead and I don't have to get a common denominator, but I'm gonna for the heck of it. Yeah, why not? So if I do that, and I multiply 1 by S plus 1 over RC1, downstairs is S plus 1 over RC1, now I get V out over V in is my transfer function. And that's gonna be equal to quantity, first it's S plus 1 over R1 C1, and then it's going to be S R2 over R1 plus S plus 1 over R1C. There's nothing tricky about this. Do you agree with me? Now I group terms. And if I group terms, I see S as a coefficient of 1 plus R2 over R1 plus 1 over RC. Agreed, class? Agreed? Here, if we go from there, we can just say that I really have. What would be the easiest way to do this? I can say that I suppose you can put the numbers in if you want. What are the values for R1, R2, or R2, R1?
R1 is 10 to the third.
Here, let me do this. R1 is 10 to the third.
C is 10 to the negative 6. R2 is 4 times 10 to the third.
4 times 10 to the third. All right, so R2 over R1 is 4, correct?
Mm-hmm.
Plus 1 is 5. Now, 1 over R1 C1. R1 is 10 to the third, C is 10 to the minus 6. You multiply them, you get 10 to the minus third. 1 over that is 1,000. Do you agree? Now, if you take a look at this, you really have 1,000 over S plus 1,000 plus, and then you have just S times 5 over S plus 1,000. Do you all agree with that, class? All right, now we can go back. I don't know how he does it, but he should have this form just before it jumps back to the time domain. Does he or not in the solution manual?
It skips over the process where he finds that. It just gives the answer.
Mm-hmm.
All right, well, I think you can all see that goes to 1,000, right? E to the minus 1,000 P U of T, right? And then this, 5 times at 5 e to the minus 1,000 T, and then it's U of T, and since there's an S in front of it, you take a derivative of that. Do you all agree with that, class? I'm going to do it that way. You don't have to if you don't want to. Plus, you can say the derivative with respect to T of, and it would be 5 times e to the minus 1,000 t u of t. And you can take a derivative. You're gonna get a delta function in there. Right? Now I'll tell you another thing to do with these. Anytime you have the same order of polynomial there, you have an s on top and s in the bottom, s squared on top, s squared in the bottom. You do this, you do long division, and I'll do it over here. For this one I had s, right, and I had 5s, didn't I? 5s over s plus 1,000. So here's what you do. You're gonna divide this into this. This is 5s. Please follow me on this one, right? A lot of people don't do this. So I have 5s here, and I divide s plus 1,000 into it. Do you all follow me? Now when I do this, what do I get? Well, s goes into 5s 5 times, right? Now I multiply, so I have 5s plus 5,000. Agreed? Take that, subtract them. When I do this, I get minus 5,000. Are you with me? That's the remainder, so that means this is really equal to 5 plus, or really minus, 5,000, and it's divided by s plus 1,000. So what I've done is decompose this by long division, so I have one term that's a constant minus the second, another term that's a function of 1 over an s plus a constant. How many understand that? It's long division. A lot of people don't think about that. You don't have to do that. If we want to do long division on that, we can. And that way, I guess it circumvents the derivative. It won't matter. So my result is 5, right? Plus, or minus actually, minus 5,000, right? Divided by s plus 1,000. Maybe you'll see this one better. Do you all agree that's legitimate? Can you see it back there? I want to make sure everybody can see. I know my writing is not exemplary. I used to get in trouble when I went to a Catholic school, and penmanship is a big deal. If you either got it or you don't, and I didn't. So if I go from the s domain back, it's a constant. Now you know delta t goes to 1. 5 delta t would go to 5. So this is delta t. Right? Now this one going back would be minus 5,000 times e to the minus 1,000 t u of t. How many see this right here? Is that the answer? Yes, because I don't know what other form he's going to put it in. He could actually add these two, make it 6,000, right? You could say 5,000, minus 4,000, correct, class? How many see this right here? How bad? Does he have minus 4,000?
I think so,
That's
yeah.
fine, but I mean, that's the same thing, right? He just grouped that.
Okay.
All right, any other questions? Important you ask them now. I gave you a fair amount, right, of homework in the process? I gave you some, I'm trying to think of all the problems I gave you circuits problems, I gave you problems with operational amplifiers, I gave you differential equations, right? And I asked you to go both get the Laplace transform, and if you have the Laplace transform, find the function, right? So we've done this pretty much, we've beaten this thing. Are there any other, we're in synthesis right now, and I'm about to cover that a little more and then show you the actual circuit elements that we'll use to do synthesis, all right? Any other questions? Okay. Just making sure everybody's trying to, that's not a bad problem. Has anybody looked at the forecast for today and tomorrow?
All sunny and cold.
Is it gonna be cold tomorrow? How cold? 60 tomorrow?
High 60.
All right, well, that's not. What's the low tonight, though?
Like 30.
A 30-degree temperature swing is a big swing. It's gonna be chilly for early morning fishing. Wow. What I'm gonna do is put over here some terms that I'm gonna keep going to. And I'm gonna just show you this. Oftentimes, we're gonna have a block that just has some constant k that you wanna multiply x in to get y. Are you with me? It's a block diagram. In x, out y, y equals kx. It can be in the time domain or in the s domain. Constant multiplication is a constant multiplication. the circuit that you can do it, now there are many, but one circuit that works, and it's very easy to understand, is just having something where I have, this is the minus terminal, plus terminal, take this and ground it, that's the operational amplifier. Sometimes you'll see op amps with this. That just means that's a power supply you connect to it. You don't worry about that for the analysis. That's more information than you need, but they put it there. Then you'll have R1 here, R2 here, then the output right here. Now this is going to be the input voltage. At this point, V out here is equal to minus R2 over R1, and I'll call it V out over V in. That's the transfer function. Do y'all agree with that?
Mm-hmm.
It's minus R2 over R1. We can prove that. We don't need to. We've seen it too often. Now, I'm going to put next the follower. This is going to have just R1 here. It doesn't have to be R1, but it can be. And goes into the operational amplifier. I mean, this is really an inverter. And now my output transfer function, H of S for this entire circuit right here, is equal to simply R2 over R1. And that's simply equal to the ratio of V out over V in. Therefore, the constant K would be R2 over R1. That is simply, this circuit right here realizes this function, this block diagram function. Does everybody see that, class? Can I get a show of hands to make sure everybody sees it? Now, you okay with it? I gotta make sure, yes, sir.
You did it twice just to get rid of the negative.
Right, and that's the inverter. Now, there's ways of doing this. There's other ways. I'm saying this is one way, but this is the simplest in terms of understanding, and it's used extensively. That's the reason I do it. This is a very common thing. The next thing is, suppose I have this. I want something where I have an output is K over S. How to implement that? Got me? So I want my output here, Y of S, to be equal to K over S times X of S. So the transfer function here is really K over S. Got me on this? This one is straightforward too. Come in with VI plus to minus V in. Now I'm going to have R1, negative, positive, ground that. This becomes a C, but this is 1 over CS is the impedance of that. Remember that. The impedance is 1 over CS, right? Now that gets fed into an inverter. And R1. And if I look at plus to minus V out over V in, which is my H of S here, that's equal to simply 1 over R1 CS, or really, it's simply the gain divided by S, where the gain here would be 1 over R1C. I want you to take a look at this. Do you all believe that? Because what? The transfer function here is this impedance, 1 over CS divided by this impedance, so it's 1 over RCS, right? But it's got a minus sign at this point. So get rid of the minus sign, we'll put it through an inverter. Now that would be the output, just 1 over R1C times S. If you...
do those second two R1s have to be R1? Like you
No,
first,
you can make
they
them, you
just...
have to make them the same value. They
Okay.
could be 1,000, 10,000, 100,000. Don't make them 0, then it won't work. All right? I mean, theoretically, yes, but you don't understand leakage currents and other problems. So you have to have some value that's above, say, 10 ohms. All right? The bigger the better, usually, by the way, for a lot of reasons. All right, now you have the elements to basically, from a block diagram, create a circuit. We're going to go through the synthesis form of it again. And this, to me, is the most interesting, because what I'm interested in, when I was where you were, I wanted to figure out how do I make a filter system, an equalizer, if you will, with a power amplifier so I could get the sound I want. And by the way, this is something, once you get the profile, the power versus frequency on your speakers, don't put them up to the point where they distort. Then once you have that function, whatever it is, you take 1 over that function and multiply it before it goes into the speakers, your sound, and then you get flat sound. I wish I'd had a couple of speakers here to show you what get dirt cheap speakers, do this on it and invert it, and then, we could do a digital equalizer, and you could see, then the sound is crystal clear, it's beautiful.
Is there like a relationship between the ratio of the resistor values on what is that one? The first op amp and the inverter?
You don't care if these values are much different than this value. It
Doesn't matter either?
doesn't matter at all. Thing is, make them something, I would say make them more than 10 ohms, all right? And I'm saying this based on practical experience, because here's what happens. For this, right, that's ground. What if you have 20 volts coming in here? All right, you're pulling amps of current. That'll heat up these quarter-watt resistors and burn them out, all right? The other thing is the input to these circuits can get overloaded too. You can fry a transistor. So you try to make the resistances high enough so no significant current is going to flow, and you don't, the resistors, the little carbon resistors that you guys have, those barrel resistors are only quarter watt usually. I don't think, once you get and you're putting watts of power through them, then those things will smoke, all right? If you get RMS 1 or 2 watts, they'll burn up, and you don't want to do that. So, practically speaking, the 10,000, 100,000 ohms is what you're seeing. And this is in the preamp stage, I should say. The final, if we were building an amplifier, the final form, the power amplifier, now that's another thing, and I do that out. I have time, I'll do it. But I love this stuff. So now the next thing we're going to do is we're going to synthesize something entirely. And first I'm going to bring it back to something. I talk about filter characteristics. I assume you know what I mean, but I'm going to just cut to the chase on this one. If you have a low-pass filter, and I'm going to need to bring you into this with an example. What it means is if we take a look at omega here, or F, and we take a look at the magnitude of 20 times the log of the magnitude of the transfer function of the filter versus S, but now we let S become J omega, then we get something like this. And this will be your magnitude A naught. And there'll be a point when it starts going down by 3 dB. Now, how many have had Bode diagrams? All right, how many have not? All right. A Bode diagram is a very powerful tool that I'll speak more of in the future. I'm going to just mention it now. A Bode diagram allows you to see the typical characteristics of filters or amplifiers or anything in a way where it's called a broken line form, right, where you're going to see a straight line and a broken line. Now, the real filter characteristics, if you're taking a look at the magnitude of this, taking the log and multiplying by 20, and this is in dB, by the way, this is in decibels in this scale. The real value would look something like this. You would have this, and then it would not go through that point. And this was called the 3 dB frequency, and I'll have to speak to this more later, just giving you an idea before we do the synthesis. And here the 3 dB frequency would be omega 3 dB. And I'll show you an example of this so you really appreciate this. Typical low-pass filter is this one, and you see it all the time. If I have a resistor R, right, and I have a capacitor C, and this is my output voltage, and this is my input voltage, then the ratio of V out to V in would be equal to H of S. Do you agree with that, class? Now, V out is 1 over CS, right? And it would be divided by the sum of this plus, I should say the ratio of this. The output voltage over the input voltage will be the ratio of the impedance of the capacitor divided by the impedance of the capacitor plus the resistor. It's simply voltage division. Does everybody understand that? And if I'm going too fast, flag me. Just let me know. So it's divided by 1 over CS plus R, agreed? Now, I'll manipulate that. I'm going to first multiply top and bottom by S. Remember, I'm trying to get it in the form I understand. So if I multiply by S, I get this. And then what I'm going to do, and I get an S here, now I divide by R. And that is typically the low-pass filter's signature for a very simple one. It's got a constant divided by a constant plus S. Now this constant and this constant don't have to be the same. the one I've showed you they are. Do you all see this? So here, if I take this function, and now I let S become J omega, and I take the magnitude of it, so I'll do it up here. If I take the magnitude of that, now I get 1 over RC, right, divided by the square root of omega squared plus 1 over RC squared. Just take a look at that for a second. Y'all see what I've done there? If I replace S by J omega, now I have what? I have 1 over RC plus J omega here, right? I need the magnitude. I got a real and imaginary number. The only way you get the magnitudes is you square the amplitude of the omega squared, square the amplitude of 1 over RC squared, and take the square root. Do y'all follow me in there? How many understand that? I have to make sure I'm not going too fast. So if I have that, now I can say, when I take 20, and I'm going to plot on this axis, 20 times the log, let me just do that here. When I take the log of this, the log, log base 10, of 1 over RC divided by 1 over the square root, or really it's going to be omega squared plus 1 over RC squared to the 1/2 power. When I take the log of that, and this is multiplying, it's log AB is log A, so it's log of 1 over RC, and then it's going to be log of this. Well, log of 1 is 0, but it's minus log of omega squared plus 1 over RC squared to the 1/2. So this is going to be minus, take a look at this, minus 1/2 log, I'll get out of your way so you can see, 1/2 log of omega squared plus 1 over RC quantity squared. Can everybody see what I've done? If I take the log of A times B, this is something people sometimes don't recall. Log, either base 10 or base E, of A times B is log of A plus log of B, right? And if I had log of A divided by B, that's log of A minus log of B. Correct, class? Y'all with me on this one? All right, so back to that. And if you have this, I didn't put that here, but if you have log, right, of anything x squared, that's equal to, you take this power out in front, so it's 2 times the log of x. Do y'all follow me? The 1/2, it was something to the 1/2 power. You pull the 1/2 in front, that's where that came from. Take this and multiply it by 20, right? So I'm going to have on this axis 20 times the log of 1 over RC. And then I'm going to have minus 10 times the log of omega squared plus 1 over RC squared, right there. If you want, you can actually leave the 1/2 inside. Maybe I will. I'm going to make that 20, and I'll leave the square in there. So it'll be square root of omega squared plus 1 over RC squared. Then, when I look at a plot of this, let me do it here. Running out of board. So this is my function. I'm going to leave the 20 out there that I want to do. And when I do it, I have 20 times the log of 1 over RC minus 20 times the log of square root of omega squared plus 1 over RC squared. And what it happens is this. When,
Since S is J omega and you square it, wouldn't that be minus?
now you don't square the J. Remember, you got a real and imaginary part in magnitude. Take a look at this.
Okay.
You've got a real A, and then you got J omega. We want this magnitude. You take this and square it, take omega and square it. We want this magnitude. right there, because of orthogonal. And actually, the way I'm doing this,
I think he's saying because J squared is negative one.
there is no j squared. I want the magnitude, I'm letting s become j omega, right? But then I want the magnitude, let me back up for a second since that's the second equation. I had something to the effect of c over as, right? A plus s, correct class? Call that h of s. Now I let s become j omega. Right? Now I want the magnitude. To take the magnitude, if I want the magnitude of this, that becomes c over the quantity a squared plus omega squared to the 1/2 power. Remember, the j omega and the a are not in the same, they're not in the same direction. You don't square the j. All right, you just take omega squared plus a squared in the square root. Do you all see that? One thing I failed to do, and I'm going to do it right here. Don't write this down, just listen. What I should have done right over here, and I'm going to do it, so you'll see this. When they're doing Laplace Bode plots, this is one of the key things. They want this term to have a coefficient of 1. This becomes important for plotting, not for doing the inverse transforms. You all follow me? Just plotting. So this will become equal to, I'll take S and I'm going to multiply it by RC. SRC plus 1 and 1 over on the top. Do you follow me on that? Now they put in, they're going to put in the omega, all right, j omega. Now you're going to get the magnitude of this, and just listen now. This will become 1 over, and then it's the square root of omega over RC, omega RC squared plus 1. Okay? Now here's why they do that. Now we're going to plot. I've got that, and I have this term here. So when I put it on this axis, just follow me now. That's fine. Follow me? Now I'm going to have minus 20 times the log of, and then it's going to be quantity omega times RC squared plus 1. All right? I don't mean to be so sloppy, but do you all see what I've done here? I've just changed the form so I have 1 as the coefficient to omega RC squared. All right? Now, why did I do that? Here's why. When I plot this, it becomes easy for plotting purposes. Remember, that's magnitude, and by the way, this would be a logarithmic axis. The paper would take the log, so this would be 10, 100, 1,000, 10,000, and so forth, all right? So it's logarithmic on this axis. On this axis, you actually do take the log. If you look at this, what happens when omega is very low frequency, very low? Well, something very small, right? Plus 1 is about 1. The log of 1 is 0, correct? So you start out with just this term. This is simply 20 times the log of 1 over RC. It stays that way until this becomes appreciable. And the point where it becomes appreciable is when omega RC equals 1, or omega equals 1 over RC. Just for the purposes of completing this thought, this is called actually, it's called the break frequency, or it's called the low pass frequency, or the cut frequency. He uses a C in his book, omega C. At that point, when 1 plus 1 is there, you're taking 20, or you're taking the log of 2 times 20, and that is 3 dB. Do you hear me on this? So when 1 plus 1 is 2, take the log of that, times 20, that's minus 3 dB. That is critical. How many hear the 3 dB point? You should hear this continually in the talks that you're around. They're saying, that's the point when all of a sudden the filter action takes over. Now it's going to start knocking off the actual magnitude after that frequency. And it'll do this. If this was the 3 dB frequency, it starts going down, and it goes down at a rate that is minus 20 dB per decade. Now, what does 20 dB per decade means? If I'm at 1,000 and I have a value of 10, a decade is 10. At 10,000, I would have 20 dB less. So if you had 40 dB here at 10, and you want 1 decade, and it's minus 20 dB per decade, you would have 20 dB left. Follow me? Another decade up, you would have 0 dB. Understand, everybody? That's 20 dB per decade roll off for low pass filter. That's a very common filter. Now, I've exhausted my class time talking about this, but what I'm going to do is this. Take these two physical circuits that you could build, theoretically at least, and now I'm going to go ahead and use the synthesis method. I don't have time today, and we're going to start realizing what transfer functions become, our transfer functions. We'll do some that will be your transfer functions. You come up with one and you can synthesize it, and that's really kind of cool, in my opinion, because this is an actual filter characteristic. You all had filters, right? Low pass, high pass, band pass. Well, with amplifiers, what I want is if I know how my speakers behave, I know what their H of S is, so to speak. I want 1 over H of S multiplying that so that now my sound is flat. Does this make sense, at least in concept? And so now I can design into my sound processing something that's going to do just that. So my speakers are going to give me perfectly flat, clear sound. And we don't have time to talk about distortion. I've got to give you a quiz, guys. All right. Everything off your desk. Take